All right, folks, now that we are experts at the cross product, let's see what we can do with it. And to do that, we're going to look at the example of calculating torque. So torque is something that we will calculate in physics fairly often. So once again, the application of doing this work with vectors is in the realm of physics and engineering. Let's get educated. The word torque comes from the Latin torquer, which means to twist. And notice as we deal with this, so we're going to have our torque wrench. We're going to have our radius r, which is going to go here. Our force is going to be exerted in this direction. Angle between them is alpha. And notice that these vectors are tip to tail and not tail to tail like our previous examples. So we're going to need to keep that in mind as we work through some things here. So we're going to indicate here, this is not tail to tail. And like we've seen when we talk about cross product, we're finding the area of a parallelogram. So let's just sketch our parallelogram here. Wonderful. All right, torque is equal to the radial vector times force, or like we've kind of seen before, we can express this in terms of vectors and magnitudes and stuff. Magnitude of the radial vector, times magnitude of the force vector, times sine theta, and the direction multiplied by the direction vector n, which is our normal vector, which is orthogonal to those two. So let's just define our tau represents torque. And in SI units, we use Newton meters. However, in your everyday life, you may also encounter foot-pounds. So especially when you work with cars, if you are tightening lug nuts for your tire, or you're talking about pressure, you might have foot-pounds. Actually, not pressure, but the torque on the nuts and stuff. So our R vector is our length of the lever. And notice it's Newton meters. That means that our lever length also needs to be in meters. F is going to be our force applied. And force is measured in newtons. So notice we're going to multiply R and F. We're going to multiply newtons in meters to get our Newton meters for our torque. And theta or alpha or whatever we're labeling it, we'll stick with theta though for now, is our angle between forces when they are tail to tail, which is not what we have here. So we're going to need to do a little bit of work. We'll also mention that as we rotate clockwise, so clockwise tightens, so righty-tighty, what you might have been told by your dad when he taught you how to use tools, or whoever taught you, or whatever context. So tightens, so as we rotate that way, the force goes into the page. So we can indicate that way. That's like that arrow going in. Counterclockwise loosens. And so the force vector would be coming out of the page. So that's our right-hand rule. As we're tightening, and you can curl your fingers around in the direction of our rotation, and our thumb points into the page. So that's our force going down. Or counterclockwise, we're rotating with our fingers. In that direction, our thumb is pointing up. The force is going up. It's loosening. All right, cool. Let's take a look at our specific example. What is the magnitude of torque produced by a 40 centimeter? Problem 1, we're given our information in centimeters. I need meters. So I'm going to convert that before I do anything else. 0.4 meters. So that we know the length of the wrench is 0.4 meters. It is applying a force of 60 newtons of force, and our angle is 30 degrees. So let's set up our situation, and then we're going to need to do a little bit of work here. So first of all, I have my wrench, my radius r, which I know has a magnitude of 0.4 meters. And then I have my force being applied. And I know that that has a magnitude of 60 newtons. But that's not the angle that I need. This is the tail to tip angle. I'm going to complete my parallelogram here. So I'm basically going to copy that F vector over here, copy that R vector over here. And what I'm going to need is this angle here. If the vectors are tail to tail, So you can just imagine I've slid my F vector down here. I've made a copy of it. And in fact, I can actually do that. Just to help you with the visual, we're going to take our force vector. It won't let me select it individually. Anyway, you get the idea. I've basically recreated this vector over here. All right. I'm going to need some information. I'm going to need to find some missing values here. I'm going to need my theta value here. What do I know about this situation? Well, I know that my theta and beta here are going to be supplementary. So theta plus beta equals 180. I know that this angle here is 30 degrees. And that means that this angle here is also going to be 30 degrees. So I can fill in that value. So theta plus 30 equals 180. So I can rearrange and solve, and I can find that my theta angle here is going to be 150 degrees. So that is the angle when the vectors are tail to tail. So tail of this vector, tail of this vector. So we have our angle. Now we can start plugging things into our formula. So tau equals radius times force vector. So we're basically finding a cross product, and we're going to find the magnitude of that cross product. So magnitude of r times magnitude of f times sine theta, where theta is the angle between the vectors tail to tail, which we just found. Let's plug in our values. Magnitude of r is given in the question as 0.4 meters. Magnitude of f is given in the question as 60 newtons. And sine theta, sine 150 degrees. From here, it's a simple calculation. We're finding that this is going to be equal to 12. And what is my direction? It's going to be my normal vector, whatever that is in this case. And while we can kind of look, we can see that our force is going like here and then here. So we're going clockwise or righty-tighty, if that helps you remember. Whatever tool helps you remember is fine. So ultimately, therefore, and it just asks for the magnitude. Technically, we don't even need the direction, but just to think about it, righty-tighty means it's tightening, it's going into the page. So in this case, into the page if we defined our plane as the page of the screen. But ultimately, see what it said, what is the magnitude? So therefore, the magnitude of the torque is 12 Newton meters.